All right, today we finished chapter 3, section 3.3, the method of Frobenius. Sounds Greek? Let's see, it says where he was from here. I don't know where he's from. He was German.
Close enough.
Okay, so we were the other day looking at solving second order differential equations using power series. Now recall what we did. We took our equation and we divided everything by a to the x, and we wrote it this way: y double prime plus b of x over a of x we called p of x, and then c of x over a of x we called q of x. And what we saw in section 3.2 is if p at 0 and q at 0 both exist, then p of x and q of x are usually analytic at 0. It's possible that p of x and q of x might both exist but not be analytic. That would be pretty rare, but it could happen. And remember what analytic means. Analytic just means that they have a power series. Then x equals 0 is called a regular point, and there are two linearly independent power series solutions centered at 0. So that was section 3.2. We found solutions at what were called regular points. And 0 was a regular point. P of 0 and Q of 0 both existed, and both had power series expansions. So what are we going to do in section 3.3?
Math centered at 0.
No, it's still going to be centered at 0.
Non-homogeneous?
No, they will still be homogeneous.
They won't be analytic?
The P of x and Q of x will not be analytic, which means 0 will not be a regular point. 0 will be called a singular point. So if P at 0 or Q of 0 does not exist, i.e. P of x or Q of x is not analytic, then 0 is called a singular point. Well, that's not quite right, because it could be possible that P of 0 or Q of 0 doesn't exist, but they could still be analytic. But generally that's going to happen. If P of 0 does not exist or Q of 0 does not exist, then that function is not analytic. It's possible that it could happen, but for us it won't. Okay, so if x equals 0 is a singular point, we're going to come back to our equation y double prime plus p of x y prime plus q of x y equals 0, and we're going to write it this way. We're going to write it as y double prime plus little p of x divided by x y prime plus little q of x divided by x squared y equals 0. If little p and little q are both analytic at 0, then 0 is called a regular singular point. And there's a technique for solving when you have regular singular points. We can solve using the method of Frobenius. And instead of writing it all down, it's in your book. So I'll just read this to you. It says, suppose x equals 0 is a regular singular point of the equation. Let rho be greater than 0 denote the minimum of the radii of convergence of the two power series for p of x and q of x. Let R1 and R2 be the real roots, with R1 greater than R2, of the indicial equation R times R minus 1 plus P at 0 R plus Q at 0 equals 0. Then, for x greater than 0, there is one equation of the form x to the R times the power series, x to the R1, and if R1 minus R2 is not 0 nor a positive integer, then there's a second answer of the form x to the R2 times a power series. So, the big things are, here is, they call it indicial equation here. We've always called it characteristic equation. This is going to be what we're going to call our characteristic polynomial. If we can solve this equation and get two roots, and the roots do not differ by an integer, then we will end up with two linearly independent solutions. Okay, so here's how this works. We have 2x y double prime plus 3y prime minus y equals 0. The first thing we need to make sure of is we need to make sure that x equals 0 is a regular singular point, which means we need to take this equation and we need to transform it to the form y double prime plus p of x over x y prime plus q of x over x squared y equals 0. And we need p of x and q of x to both be analytic. So what steps would you go through to take this equation and put it in that form? Divide by 2x. That's y double prime plus 3 over 2x y prime minus 1 over 2x y equals 0. Okay, that's y double prime plus, I'm going to write this as 3/2 over x y prime. Why am I writing it as 3/2 over x? It fits the form something divided by x. So 3/2 divided by x. So there's my p of x, and I divided it by x. Minus I want this one to be something over x squared.
1/2 x. 1/2 over x squared.
1/2 x.
Wait, what is that?
Well, what happens when you take 1/2 x and divide it by x squared?
Oh, I see.
The x is reduced, you end up with a 1/2 over x. That's 1 over 2x. Y equals 0. Okay, so now I think we have it written in the right form. Is 3/2 an analytic function? Does 3/2 have a power series expansion?
Yeah.
Yes, what is it? 3/2.
Yeah.
It's a pretty easy power series expansion. Does 1/2 x have a power series expansion? Yes. What is it? 1/2 x. The power series expansion for a polynomial is the polynomial. So these are both analytic at 0, and so the method of Frobenius should work. Next, we need to compute our characteristic polynomial. The characteristic polynomial is r times r minus 1 plus p at 0 r plus q at 0 equals 0. That's r squared minus r plus, what's p at 0?
Yeah.
3/2. 3/2 r plus, what's q at 0? It's 0 because I'm plugging in 0 for the x.
Oh.
1/2 times 0 is 0 equals 0. This is r squared plus 1/2 r equals 0. So r times r plus 1/2 equals 0. I get r equals 0, r equals negative 1/2. We got two solutions. Do these two solutions differ by an integer? No, in fact, they differ by a half. So since these two solutions differ by a half, we are guaranteed two linearly independent solutions.
So they have to differ by a half?
No, they have to differ by not an integer.
Oh.
So if this one were 0 and this one were negative 2, we would not be guaranteed two linearly independent solutions.
Oh.
So the r times r minus 1 equation, that's just straight from the book?
That's straight from the book. Yep. So it's always r times r minus 1, p at 0 r, q at 0.
So those two r values are telling us that we have two linearly independent solutions?
Correct. These two r values tell us that we have two linearly independent solutions. Again, if this one were 0 and this one were a different integer, if this one were 0 and this one were 3, we would not be guaranteed two solutions. They have to differ by not an integer.
What if it differed by like 4 fifths, or 5/4?
Is that an integer? Is 5/4 an integer?
Well, it'd be like a mixed fraction thing.
Is 5/4 an integer?
No.
No, so we would be okay,
Okay.
as long as they don't differ by an integer. So if this one were 1/2 and that one were negative 1/2, that would be no good because they would differ by 1. So you need them to be differing by not an integer. Okay, so what that tells me is there are two solutions that are going to have the form x to the r, the sum n equals 0 to infinity of a sub n x to the n. What I'm going to do is I'm just going to deal with the power series once. I'll take my derivative, I'll take my second derivative, I'll plug everything in, and then later on I'll plug in r equals 0, and later on I'll plug r equals negative 1/2 in. That way I only have to do it once. If I start with r equals 0 here, then I have to take the derivative, take the second derivative, plug it all in. And then if I plug in r equals negative 1/2 at the beginning, I got to take the first derivative, second derivative, plug it all in. I got to do all that work twice. I don't want to do all that work twice. I only want to do it once. Before I start taking derivatives, I'm going to write this as the sum from n equals 0 to infinity of a sub n x to the n plus r. So I took this x to the r, I brought it inside, which forced me to add my exponents. Now I take the derivative. Y prime is the sum from n equals 0 to infinity of, I'm going to bring the n plus r down, a sub n, x to the n plus r minus 1. I was hoping somebody would ask, shouldn't it be n equals 1? Okay, so do you remember back before we had our series was the sum from n equals 0 to infinity of a sub n x to the n. And when we took the derivative, we brought the n down, a sub n x to the n. So what happened here if we plugged in 0? We got 0, so we didn't need the 0 term. So we when we had this, when we brought the n down, subtracted 1 from our exponent, when we plugged 0 in, we got 0. So we didn't need the 0 term, so we chose to start at 1. I could, if I wanted to, start at 0 and it would still be correct, wouldn't it?
Yeah.
But notice for this one, when I take the derivative, if I plug 0 in, am I going to get 0? No. So this one has to still start at 0, unfortunately. And the same thing's going to happen with y double prime. Again, back here, when we took the second derivative, we would bring down this n minus 1. So when we plugged in 0, we got 0. When we plugged in 1, we got 0. So we chose to start at 2. Can't do that anymore. Got to start at 0. All right, so y double prime is the sum from n equals 0 to infinity. I'm going to bring down the n plus r minus 1. I already had an n plus r. I had an a sub n, x to the n plus r minus 2. Now I'm going to plug in. So I have 2x times my second derivative. So 2x times the sum from n equals 0 to infinity, n plus r minus 1, n plus r, a sub n, x to the n plus r minus 2. Minus 3 times my first derivative. My first derivative was the sum from n equals 0 to infinity, n plus r, a sub n, x to the n plus r minus 1, minus my original function. My original function was the sum from n equals 0 to infinity, a sub n, x to the n plus r equals 0. I'm going to take this 2x and I'm going to move it in there. What happens when I take that 2x and I move it in there? I get n plus r minus 1 because I have a minus 2 there and I'm adding 1 in there. Okay, so I got to rewrite this whole thing again. This is the sum from n equals 0 to infinity, 2 times n plus r minus 1, n plus r, a sub n, x to the n plus r minus 1, minus the sum from n equals 0 to infinity. I'm going to slide that 3 inside too, but that doesn't change any of my exponents. 3 times n plus r, a sub n, x to the n plus r minus 1, and finally minus the sum from n equals 0 to infinity, a sub n, x to the n plus r equals 0.
Hey George, in that second one there with the 3, isn't that supposed to be a positive, or is it negative second or a radial function?
Oh, it should be a positive, shouldn't it? Yeah, I copied it down wrong because my original equation had a plus on it. So yes, that should be plus there. So this should be a plus 3 right here, And that should be a plus right there. Thank you, Liam. Somebody's paying attention. That's right. Okay, next. I look at my exponents. Here I have an n plus r minus 1. Here I have an n plus r minus 1. Here I have a n plus r. They don't all match. So what am I going to do? Give up. No, I'm not going to give up yet. Not yet. Soon, maybe, but not yet. All right, typically what you want to do is you want them to all be the same. Typically, you make them all be the smallest one that you see. So of n plus r minus 1, n plus r minus 1, n plus r, which one's the smallest one? N plus r minus 1. So I'm going to leave this one alone. It's already got an n plus r minus 1. That one has an n plus r minus 1. So what do I have to do with this one? I have to subtract 1 here, subtract 1 there, and then add 1 there. All right, so I have to write it all down again. Sum n equals 0 to infinity. 2 n plus r minus 1, n plus r, a sub n, x to the n plus r minus 1, plus sum n equals 0 to infinity. 3 times n plus r, a sub n, x to the n plus r minus 1, minus the sum from n equals 1 to infinity, a sub n minus 1, x to the n plus r minus 1, all equals 0. Okay, here comes a new wrinkle. All the powers match, right? But the bases don't match. This one has a 0, this one has a 0, this one has a 1. Can I just change this one to a 0? No, I cannot just change this one to a 0 this time. Why not? Because there's no n in front of it, I won't have 0. I need them to all start at the same spot.
Bring the other one to 1.
Nope, I'm not going to bring the other one to 1. What I'm going to do is I'm going to take this one and I'm going to plug in the number 0 and I'm going to write it down. And then everything left would start at 1. And I'm going to take this one and I'm going to plug in the number 0. And then the whole rest of the thing would start at 1, and then this one already starts at 1. Okay.
Oh, that's where we get the r and the r minus 1.
That's where we get the r and the r minus 1, correct. Okay, so what happens if I plug in 0 right here? Remember, I'm plugging 0 in for n. If I plug 0 in for n, I've got the 2 times r minus 1 times r, a sub 0, x to the n minus 1. R minus 1, I'm sorry. R minus 1. I'm going to plug in 0 for this one and write it right next to this too, just to have them together. And then I'll write both the sums starting at 1. I plug in 0 for this one, I'm going to have plus 3r, a sub 0, x to the r minus, plus everything else, all the 3 sums, and now all the 3 sums start at 1. Sum n equals, I'm going to blow out the ink in this pen just in one day. 2 times n plus r minus 1, n plus r, a sub n, x to the n plus r minus 1, plus sum n equals 1 to infinity, 3 times n plus r, a sub n, x to the n plus r minus 1, minus the sum n equals 1 to infinity, a sub n minus 1, x to the n plus r minus 1. All that, all combined, gives me the nice little number 0. Okay, we're getting close. What has to happen now? Well, what has to happen is these two need to add up and give me the number 0. And then all of these things combined, these three series combined, they need to add up and give me the number 0 also. Now, do you remember what our R numbers were? 0 and -1/2. There they are.
I say we start plugging in 0.
Notice, if we plug 0 in for R, what do we get right here? That's 0. So that's good. We don't have to worry about it when R is 0. It's already going to be 0. What happens if R is -1/2? Well, let's see. What's -1/2 minus 1? What's -3/2 times 2? -3. What's -3 times 1/2? Times -1/2. That's going to be 3/2. And then when I plug in -1/2 there, I'm going to get -3/2. So I get 3/2 that thing plus -3/2 that thing. It adds up to 0. That will not always happen. If that doesn't happen, that's very easy. It just means that A0 would then have to be the number 0. So there's two possibilities. Possibility number 1, you plug in your two R numbers and you get 0 both times. You're fine, nothing to worry about. If you plug in your numbers and you do not get 0, that's also fine. It simply means that A0 would have to be the number 0. Those are the only two possibilities. So, this piece is good. This piece we're happy with. For our two R numbers, it's already going to add up to 0. We don't have to do anything with it. We can leave it alone. Now, all these series, how do those add up and give you the number 0? Everything inside has to add up and give you the number 0. And notice again, everything inside has an x to the n plus r minus 1. I can factor that out and cancel it. So when I write down my coefficients, I'm not going to bother writing the x to the n plus r minus 1. I can divide them out. So we have maybe so you can see what I'm writing. Two times n plus r minus 1 times n plus r a sub n plus 3 times n plus r a sub n minus a sub n minus 1 equals 0. Absolutely. Why do you want to solve for a sub n minus 1?
That's what we always do.
Because it's the different one, or it's the smallest one. You always want to get the different one all by itself. Before, when we did these, the different one was always a sub n plus 1. Now the different one is a sub n minus 1. Well, the good news is, pretty easy to get that by itself, isn't it?
Yeah.
All right, so a sub n minus 1 equals 2 times n plus r minus 1 times n plus r plus 3 times n plus r all times a sub n. So I added the a sub n minus 1 to the other side, and then I factored out the a sub n. Now remember, we have two numbers for r. We have our recursion relationship. Now I want to plug in my r number. Which one do you want to plug in first? 0. Okay, if r equals 0, I get a sub n minus 1 equals 2 times n minus 1 times n plus 3n a sub n, which is 2n squared minus 2n plus 3n, so that's going to be plus n, a sub n. So what happens when n equals 1? I get a sub 0 is no, I want it to be an n this time because it's going to work out nicely. If n equals 1, a sub 0 is 3 a sub 1, which means a sub 1 is 1/3 a0. So this time, see how nicely it works? When I plug in n equals 1, I actually get the a sub 1. That didn't happen before, but it happens here. N equals 2. If n equals 2, I get a sub 1 is, I plug in 2, 2 squared is 4, 4 times 2 is 8, 8 plus 2 is 10, 10 a sub 2. So a sub 2 is 1/10 a sub 1, which is 30th a sub 0.
So no matter what the power is in the end, we always just count up by one. Like before we had to split them up if there was two solutions.
Correct. We're going to get two solutions this time. We get one solution by plugging in r equals 0, and then in a minute I'm going to have to repeat this whole process but plug in r equals -1/2.
Well, when we check n equals 1 equals 2, we're going to count them up regularly. We're not going to split them up into odd and even.
Correct. We do not need to split into odd and even because we're going to get our two solutions based on the r numbers. All right, let's do one more. If n equals 3, I get a sub 2 is 3 squared is 9. 9 times 2 is 18. 18 plus 3 is 21. A sub 3, which says a sub 3 is a2 over 21, which is a0 over 21 times 30. 630. Do you happen to see a pattern in the numbers? 1/3, 1/30, 1/630. They do all have 3's in them, that's true. My answer would have been they all have 1's on top. Other than that, no, I don't know how we're going from 3 to 30 to 630. So again, we're going to write our answer this way. Our answer is y equals, remember our answer was x to the r, the sum from n equals 0 to infinity of a n x to the n. But in this case, r is 0, so x to the 0 is going to be 1. So we're just going to have a0 plus a1 was 1/3 a0 x to the 1, and a2 was 1/30 a0 x squared plus 1/630 a0 x cubed plus ... And if somebody wants to plug in more numbers and get more fractions, they're welcome to do so. I think having 4 terms of the power series is plenty. All right, almost done. I got to find my other solution. So that one's y sub 1. So now I got to come back up here to my recursion relationship, and I got to plug in -1/2 for my r number. So I'm going to have a sub n minus 1 equals 2 times n minus 1/2 minus 1 times n minus 1/2 plus 3 times n minus a half a sub n.
George, can you start out please?
Better? All right. In the interest of time, because I'm running short of time here, you can trust me on this. If I FOIL these together, multiply the 2 through, multiply the 3, 2, add up all my like terms, I got 2n squared minus n a sub n. And then I start plugging in numbers. Yeah, I don't know if they will always be related. I mean, these two, one of them turned out to be 2n squared minus n, and one of them turned out to be 2n squared plus n. I don't know if they always come out that way or not, or if that's just a happy coincidence with this problem. N equals 1. A sub 0 is, when I plug in 1, I get 2 minus 1. That's 1, so I get a sub 1. If n equals 2, I get a sub 1 is 2 squared is 4, 4 times 2 is 8, 8 minus 2 is 6, 6 a sub 2, which says a sub 2 is a 1 over 6, which is a 0 over 6. And once again, we'll do one more. When n equals 3, I get a2 is 3 squared is 9, 9 times 2 is 18, 18 minus 3 is 15, a sub 3.
George?
Yes?
A sub 0 and a sub 1 are equal when a sub 2 is a6, a sub 0, a of 0.
Well, but I needed to get the a sub 2 by itself.
Okay, we're good.
So I got the a sub 2 by itself by dividing by 6, and then I plugged in the a1 equals the a0. I'm enjoying my fractions here. Don't take them away from me. Equals a0 over 6 times 15, 90. Okay, so here's my other solution. My other solution is y sub 2 is x to the negative 1/2 times a0 plus a1x, or a0x, plus a2 was a0 over 6 x squared, plus a0 over 90 x cubed, plus dot dot dot. Now, I did make one mistake. It's not a serious mistake. If I used a0 here, I shouldn't have used a0 here. What should I have used? Any other letter. This a0 and that a0 are not necessarily the same. Depend on your initial conditions. Should have used a different letter, but that's okay.